Hi guys, so today I'm going to be talking about chapter 5 of which is chemical energetics, and I will first get started by saying what is enthalpy. Enthalpy is the total energy content of reacting materials, and it cannot be measured. So it is basically when a chemical reaction is occurring in a system, we cannot possibly measure the energy present in that reaction. But what we can actually measure is the change of energy that is occurring from chemical energy to heat energy as the reactants are reacting to form products and heat energy is given out. So we can measure the change in terms of that. So enthalpy changes. So enthalpy change is symbolized with like delta H, and it is the measure of energy transferred from known amount of reactants, which is measured in units of kilojoules per mole. Next, so to measure enthalpy change of combustion, as an example, we can set up a calorimeter in which there's a beaker of water being heated by a spirit burner which contains a known amount of fuel, and the beaker will contain a known amount of water. So then we can, with a known amount of water, and by measuring the temperature change in the experiment, and also the change in mass of the fuel being used, and how much of the fuel is being combusted can be calculated, and then also the chemical molecular formula of the fuel being used, then we can use this to calculate the mole of fuel that is being combusted, and then also the specific capacity of water, which is symbolized as C, and then we get this 4.18 joules per Kelvin per gram value from our data booklet, and it's a constant. So we can use E equals to mc delta T to calculate the energy used to change temperature of that amount of substance. So by using this equation, we can substitute M, which is mass, substitute C, which is the specific heat capacity of the substance, and then delta T, which is the temperature change. So then by dividing this energy with the number of moles of the fuel being combusted, which is what the definition of standard enthalpy change of combustion refers to the mole of. So it is the enthalpy change when 1 mole of substance is completely combusted under standard state conditions. So then you can use you need to divide the energy by the mole of fuel being combusted. So then we can find the mole of fuel being combusted through a series of data that's being given from the questions or we obtain from the experiment. But here, for example, let's just say mass over mR. Then we can find mole, and then we can substitute it into the E divided by mole, and then we can calculate for the enthalpy change, which is measured in kilojoules per mole. Next is that we can assume that 1 cm cube of water is equals to 1 gram of water. So depending on which sort of data is given in the question, then we can use this assumption in water and aqueous solutions when calculating for the enthalpy change. Next is that enthalpy changes can be positive and negative. So a positive enthalpy change indicates that energy is absorbed from the surroundings, which means it is an endothermic reaction. And an enthalpy change can be also negative, which means the energy is being released to the surroundings and therefore can be exothermic. So these enthalpy changes can be represented in energy profiles, which you can see below. So we can see that in an exothermic reaction, as energy is given out to the surroundings, so therefore from reactant to product there is a decrease in energy, which you can see by the arrow over here, and then so it's a decrease of energy level from the reactant to the product. In an endothermic reaction, however, a rise in the energy level from the reactant to the product, so that you can see the rise over here, and it's a positive enthalpy change. And also in blue, you can see that I have drawn the reaction pathway in which the chemical reaction takes during a reaction in terms of the energy levels. So then you can see that the activation energy is labeled here, and is here and here. And then it is basically the amount of a minimum energy needed to start a reaction. So then the reaction can be endothermic or exothermic, but it still requires a minimum energy to start this reaction. Next is that standard enthalpy change of reactions, but standard means that when measuring them, we are under standard state conditions, and under standard state condition means that it is under a pressure of 100 kilopascals or 1 atmospheric pressure. It is at a temperature of room temperature, which is 25 degrees Celsius or 298 kelvins. And then the reactants is at a physical state that is the most stable state that the substance is in under standard state condition. And also the solutions under standard state condition must have concentrations of 1 mole per dm cube. Next, 6 types of enthalpy changes are in our syllabus, and I will go through them one by one. First is the standard enthalpy change of formation is symbolized by this, and then it is the heat change required to produce 1 mole of compound from its pure elements measured under standard state condition, which means that the elements at this standard state condition, the most stable physical state, is formed into a compound. So they combine together to form a compound. So it is usually negative because bond forming is releasing energy, and usually it would a net enthalpy change of negative because energy released in bond formation is usually more than the energy used in bond breaking, because this is the standard enthalpy change of formation as compounds are being formed. So it is usually negative but can be positive. Next is the standard enthalpy change of combustion. It is when the heat energy evolves when 1 mole of substance is completely combusted in excess oxygen measured under standard state conditions. This means that 1 mole of something is completely combusted, which means it must be producing carbon dioxide and water in excess oxygen. Enthalpy change is always negative because heat is evolved during combustion because it is burning something, so it must necessarily be releasing heat energy out to the surroundings, and therefore it must be negative enthalpy change, and it is exothermic reaction. Third is the standard enthalpy change of hydration, which is the heat energy evolved when 1 mole of separate gaseous ions is dissolved in water to give an infinitely dilute solution measured under standard state conditions. So infinitely dilute solution is basically a solution that is so dilute that it can no longer be dilute. Like even further dilution of that solution would give the same energy change. As you can see here, gaseous sodium ions are dissolved in water, which is represented by AQ over here, which means aqueous, and then it forms a sodium ion that is in aqueous state. So then it is always negative because when ions are dissolved in water or basically hydrated, intermolecular forces are formed between ions and water molecules. Hence it is the same concept as bond formation, so energy released, so it's exothermic, so it's a negative enthalpy change. Number 4 is the standard enthalpy change of solution, and it is the heat change when 1 mole of solute dissolves in water to give an infinitely dilute solution. It is measured under standard state conditions. As you can see here, we have salt, NaCl, dissolved in water to form its aqueous ions individually. So then it is a bit similar to hydration in terms of like the name, and it can be a bit confusing, and also that both is dissolved in water to form infinitely dilute solution. But hydration is always pertaining to gaseous ions, and how I form an image in my mind about this is that hydration is always relating to something about vapors and always something about gases. But solution is always something that is solid, a solute that is dissolved in water. So it's a solid rather than a gas. I picture like salt dissolving in water usually, and that's how I differentiate between the two. And then so this standard enthalpy change of solution can be positive or negative. It's the standard enthalpy change of neutralization, which is symbolized by this. It is the enthalpy change when 1 mole of water is produced when H plus ions from an acid is completely neutralized by the OH minus ions from an alkali. So this is the reaction equation that we would write for any type of neutralization, but in this case the example is least specific alkalis and acids. But in an overall ionic equation, all of the reactions of neutralization would give this equation, because the spectator ions cancel out, and therefore it's only left with these only. When you're asked to write an equation, ionic equation, overall equation, you can write this equation only. Next is the standard enthalpy change of atomization, which is symbolized by this, and it is the enthalpy change when 1 mole of separate gaseous atoms of the elements are formed from its elements under standard state conditions. It is basically when some element is forced into being a gaseous state from its most stable physical state under standard state conditions. So it must be forced to become into a gas state, and also in the same time, the second action is that it would be forced into being an atom form if it is not already in an atom form under standard state conditions. When it is not naturally occurring as an atom, it is forced into becoming an atom. So as you can see here, iron is from a solid is forced into become into a gaseous state by taking in energy, and here is chlorine molecules are turned into chlorine atoms, but it is already in gaseous state, so therefore there's no action in terms of changing the state. So here it's also energy is taken in to break the bonds between the molecules to form chlorine atoms. and therefore it is always a positive enthalpy change because the action is breaking bonds or overcoming forces, breaking bonds in terms of changing molecules to atoms, and overcoming forces in terms of changing the solid states to gaseous states, and therefore energy is always needed for that, so it's a positive enthalpy. Next is bond enthalpy, in which we know as the amount of energy needed to break one mole of specific covalent bond. Bond making is negative because energy is released and therefore is always exothermic and a negative enthalpy change. Bond breaking is always needing energy, and energy is therefore absorbed and therefore is positive enthalpy change. And we can measure standard enthalpy change of reactions through using the energy that is absorbed in the reactants when they are breaking the bonds, because in the reactants the bonds are being broken between the molecules, so then they can rearrange the atoms to form the products. So then therefore bond breaking occurs in the reactants part and bond making occurs in the products part, where the broken atoms are now bonded together in a different arrangement to form the products. So the energy absorbed for bond breaking minus the energy released for bond making, that is the enthalpy change of a reaction. So average bond enthalpies are what we know as the values in our data booklet. So these average bond enthalpies have features which can be a disadvantage. So all values are positive as data is collected of only bonds being broken, but we can also derive that since energy is conserved, the bond forming would have the same energy release. 2 is that average bond enthalpies are average values. The actual values actually differ between different molecules because different molecules will have different atoms bonded to that same bond. 3 is that they are measured for bonds in gaseous compounds only, so this means that in our physical states, the bond enthalpies can vary. And these average bond enthalpies are very difficult to directly obtain experimentally, so therefore we often calculate these values using Haas law, and therefore it may not be exactly accurate. So for example, here is a question that we might be asked in the exam to calculate the standard enthalpy change of this reaction. So we have this reaction over here. What I would do is first draw the displayed formula of these covalent compounds, so then I can easily just count how many of these bonds are there and then substitute the values from the data booklet. So here is 1, 2, 3, 4 NH bonds, and then then 1 NN bond, 1 OO bond, and 1 N2N bond, 4 O2H bonds. So then we can put it into the equation in which energy absorbed for bond breaking in the reactants part is minus with the energy released during bond making in the products part. So then we can get all these values of bond enthalpies from the data booklet and then just substitute them in and then get the answer. Next is Haas law, in which it states that if a reaction can take place by one or more routes, the overall heat energy change is equal to the sum of the heat energy changes of all individual steps. This is basically a description of the conservation of energy, but only when the initial and final conditions are kept the same. So like if we cannot measure a enthalpy change of a reaction experimentally, we can measure through other enthalpy changes of different reactions that might have relationships with the reactants and products of the reaction that cannot be experimentally measured. Then you can connect them in terms of forming a relationship, and then those reactions that can be experimentally measured up, and then you can get the enthalpy change as well indirectly. So next is an example. So calculate the standard enthalpy change of formation of this, and we are given all the standard enthalpy change of I'll just say enthalpy change of combustion because it's too long. Enthalpy change of combustion of carbon, enthalpy change of combustion of hydrogen, enthalpy change of combustion of methane, and these are all the reactant and products of the chemical equation that we need to find the enthalpy change of formation for, which is the enthalpy change of formation of methane. So what we need to do is that we can link all of these equations together, as we can see that all of these products formed are either carbon dioxide or water. So then we can connect them by drawing arrows towards the product. Carbon is combusted to carbon dioxide, enthalpy change of combustion of carbon over here, drawn arrow here to connect. and then standard enthalpy change of combustion of hydrogen, but you need to times 2 to it because the definition states that it is 1 mole of substance that is being combusted. So here is actually 2 moles of hydrogen being combusted, as this is what is required in the mole ratio of the reaction that we are trying to find for. So this reaction, so then we need to account for that extra mole. So then we connect it here, and then we have 2 times of this value. Standard enthalpy change of combustion of methane is here, and we connect it this way because it's combusted to form carbon dioxide and water. In order to form an equation, we need to swap this direction of this arrow so that it can go this way, this way, this way, so that it can have an indirect route. So then the standard enthalpy change of formation of this reaction would be standard enthalpy change of combustion of carbon plus enthalpy change of hydrogen, 2 times of that, and then minus because we want to flip the direction, so then it's minus the standard enthalpy change of combustion of methane, and then you substitute all these values that are given, and then obviously be careful of the negative and positive signs, and then you can get the answer. So the remarks I want to make when tackling Hess law cycle questions is that we need to take care of the mole of reference of the definition when we calculate using Hess law. So we need to multiply the enthalpy changes with what is necessarily to account for the mole ratio in the reaction that we need to accommodate for. We need to take care of the moles that we need to multiply. Also, if the directions of the arrows are not the way we want it to form the indirect route, to flip it, we need to times a negative to it. Next, so I'm going to talk about energetic stability, and it is a description of relativity, which means it must be in comparison to something else. So you cannot say something is energetically stable, but you can say something is energetically stable relative to something else. Something is energetically stable means that they have a lower energy level. So they have a lower energy level, which would mean that they have a lower position on the energy profile. And why they are energetically stable when they are at a lower energy level is because it's harder for them to lose more energy again to form a more energetically stable product. So then, therefore, it is more energetically stable relatively to something else. So in terms of this, we normally would compare the energetic stability of products relative to reactants. Kinetic stability is also something we use in chemistry a lot. So if it is different from energetic stability, if something is kinetically stable, it means that there is not enough energy to collide with each other to overcome activation energy, which is the minimum amount of energy needed to start a reaction. Relationship with the standard enthalpy change of formation with the relative and energetic stability. So as most compounds are formed exothermically, because which means they have an enthalpy change of formation that is negative, because normally it would be energy released in bond formation is normally larger than the energy absorbed for bond breaking in a enthalpy change of formation. So products is therefore produced at a lower energy level, which means a lower part of the energy profile, and therefore it is energetically stable relative to the reactant. So then when there is a more negative enthalpy change of formation value, which that would mean that is a more lower energy level, and that means that it is more energetically stable than the reactants, because the more lower it is at a lower energy level, the more harder it is for it to lose more energy to be at a much lower energy level, so therefore it's very energetically stable. So an example here is carbon in terms of diamond and carbon in the form of graphite, and it has a standard enthalpy change of formation of -2 kilojoules per mole. And then so carbon in the form of diamond, it is energetically unstable, so it has a tendency to decompose into the more stable product, which is the carbon in the form of graphite. But it doesn't occur, as we know, we do not observe this, so it doesn't occur because it is that diamond is kinetically stable, which means it does not have enough energy to collide with each other to overcome the activation energy, which is the minimum energy required to start that reaction. So something can be energetically unstable and wanting to decompose into a more energetically stable state or product, but it may not have enough energy to overcome its high activation energy, as it has a very high kinetic stability. And that's it for me. Thank you.